All right, this has got to go fast. That's Sonic, in case you didn't know. And then who am I? I'm Luke Parham. I work at a company called Fusion. I'm an iOS engineer there. And Fusion is kind of like a 3D photography company. I'll show you that in a second. And then I also write tutorials for raywonderlake.com. I do some videos for them, too. And so this is a fuse. This is the Kubo Witch. And this is like a regular picture, but you can touch it, and you can move it around and look inside it. So it's kind of a cool little 3D format. And then, so I work on the renderer in iOS. And as you can imagine, if you have a bunch of these in a feed, and you're scrolling it around and moving them all, it can be kind of a performance-sensitive thing. So this is just talk of some of the things I've learned along the way while I've been working on this. So why should you care about performance? Well, for that, I have a little story. Once upon a time, there was this team working on the Macintosh. And it was all going great. It was way better than the Mac 2. But there was one problem, and that was that the boot time was actually just as slow as the old Apple II was. And the reason for this was some disk problems. They couldn't get it to go as fast as they needed to. And one guy, Steve Jobs, was not happy about this. And so he came and talked to the engineers, and he gave them a little pep talk. And he said, let's say you can shave off 10 seconds of the boot time. If you multiply that by 5 million users, that's 50 million seconds every single day. Over the course of a year, that's probably dozens of lifetimes. So if you make it boot 10 seconds faster, you've saved a dozen lives. That's really worth it, don't you think? And this is kind of a funny story, because by that logic, we could all delete Twitter and save millions of lives. But it's still fun to think about when you're thinking about this performance stuff. So what's the game plan for today? We're going to talk about how you can notice dropped frames. So this is kind of the telltale signal of your app being a little too slow. We'll use a CA display link for that. And then we'll talk about some of the tools, time profiler, the core animation instrument, and then activity trace. I won't go into this time, didn't have time for it, but it's also pretty nifty. And then at the end, we'll have a bonus level where we just talk about some extra performance tips and stuff. So dropping frames. This is a pretty important thing when you're thinking about performance. So in general, on iOS, the first thing you want to think about is the main thread. This is kind of where you always end up starting when you're thinking about performance. And the main thread is responsible for two things. First, it's responsible for taking in user input. So this is taps, motion, swiping, and all that stuff. And then in response to that, it will display results to the screen. So it does drawing, and all of this happens on the main thread. And this is, of course, a single thread. And so when you block this, you end up dropping frames. That means that you have a main thread, and it draws 60 times every second. And if you're doing too much work on that main thread, it'll just skip that drawing for that 16 millisecond interval. So your goal should be 60 FPS on any device that you support. And this is even iPhone 5, iPhone 4S if you're still there. So the goal is any chunk of work you do, make it fit into this 16.67 millisecond amount of time that you have to draw each frame. On the iPad, of course, it's even shorter than that. And the other thing you should think about is speed. So this is the general speed of a piece of code versus perceived speed, which is also called responsiveness. So responsiveness is just how does your app feel to your users? When they tap a button, do they have to sit there and wait for it to push a view controller? That can all kind of contribute to how good your app feels to a user. So dropped frames and blocking interactions, these create a perceived slowness in your app, even if particular code happens to be fast. So to fix this, make things more responsive, a lot of times you can just rearrange work. You can get it off main, even if you can't quite figure out how to get it to be faster. But anyway, rule number one is you can use a CA display link to track dropped frames. There's also another way that's a little easier, but this is a very exact way to track when your app is dropping frames. So a CA display link is basically a special timer. It fires on the vsync of your app. So the vsync is when your app is drawing to the screen. So you can it's just like anything like a gesture recognizer. You set up this display link, and then you give it a method to call. So every time the screen gets drawn to, we'll call this update method. And then we'll do a little bit of math. And then the important part is if the elapsed time, since the last time the screen was drawn to, is greater than 16.7 milliseconds, that means your app has been dropping frames in that interval. So you can print when this happened and how long of a gap there was. And that way you can kind of see how many frames you've dropped. You can do more math than this. You can get averages, like your FPS per second and all that stuff. So pretty nifty. So just a quick example. There's an app called Catstagram that I made, pretty similar to another app. But and then here you can see the logs just printing out every time your system is dropping frames. And if you look closely, you can see when images pop in, you kind of get a big stutter. So then you can see that in your logs, which is pretty nice. OK, so now we're going to talk about Time Profiler. Now that you know when your app is dropping frames, where you have problems at, now you can actually use Time Profiler and track things down. So this is an example trace. As you can see, it is very lovely. There's a lot going on here, but the important part to look at first is the call tree. And this is basically a big list of methods you can dig into. And let's go ahead and look at how that works real quick. So with the call tree, in general, you have an app, right? And the main method is where everything originates from. When you're using Time Profiler, it actually injects itself into the run of your app. And then at a constant interval, we'll say like 1 millisecond here, it'll take a snapshot of your call stack. And then over time, it generates this call tree. So let's say we're 1 millisecond in, takes a snapshot. We have main calling foo, calling bar. We take that, we put it in our tree. And now we have one main, one foo call, and one bar call. So then 1 millisecond later, takes another snapshot. Here we have the same call stack. So we just put it over there and bump these numbers up. So they've each been called twice now. Then on the 3rd millisecond, we have a different call stack. We have main calling bar directly. So this means that our call tree now has a branch. We have main calling foo, and then sometimes main calls bar. So as you can see, main's number was bumped, and then bar was put as a new branch. And then finally, we have main calling foo, calling another method called baz. And the interesting thing here is that baz has actually already been called twice, but it's such a short method that it rarely shows up in these traces when it gets taken. And this is actually by design, right? When you do a Time Profiler session, you're actually kind of getting a feel for what percentage of the time a given method shows up in these traces. So if you have a method that's short enough and fast enough, it won't show up at all, which is great because it clears out a lot of noise that could, fill these call stacks up. So then we make one more branch, and our call tree is built. So now that we've seen that, we can come back into Time Profiler, and we can go to the console. And there we can see all the dropped frame messages that we've printed out earlier. Then you can just say, like, for instance, in this example, oh, we're dropping a bunch of frames 11 seconds in. Let's look at our timeline window and see, oh, well, this is a bunch of work happening. So let's see what's happening there that's causing these frames to be dropped. So you can click and drag, and that'll highlight just that area on the timeline. And then everything in the call tree will be just the things that were called during this time that you've kind of pared it down to. And then in general, this is kind of your home base. Whenever you're in these profiles, pretty much guaranteed every time you'll have main thread, main, and then it'll go down to this CF run loop run section. So let's see. Basically, yeah, you'll see this, and it's kind of overwhelming at first. At least I would look in here and be like, I don't really know what's going on. But it's kind of one of those things where the longer you just look at it and get used to it and kind of Google what things mean, you eventually kind of get comfortable with seeing this kind of stuff in there. So if we look at the first one, we have CF run loop run, and then we have the callbacks that the run loop has. The first one is doing observers. So let's drill down into that one. And if we do, once again, we see a bunch of Apple code, a bunch of CA transaction stuff. And this is another example where it's easy there's actually an option where you can hide Apple libraries and not see any of this. And it's pretty easy to come in here and see this and be like, I didn't write this code. Nothing in this stack is something I did. So I'll ignore it. I can't fix this. This is no big deal. But really, that's kind of a dangerous thing, especially in this case, because you can miss very obvious, big performance problems in your app. So if we kind of zoom in here and read through all these, we see that eventually it starts talking about JPEG decoding and image stuff. And if we come to this, we see there's an Apple JPEG decode image all, and it's taking 32% of the time on our main thread. And this is happening during this area where we're dropping all these frames. So we can be vaguely certain that this is the reason that these frames are getting dropped. So rule number 2 is if you can, you should decode JPEGs in the background, especially if you've taken a trace and you see that this is a reason that your app is dropping frames. To do this, all you have to do is use core graphics. It's not the prettiest thing, but it's not super crazy. You just make a context, draw your image into it, and then use that new. And whenever you draw an image into a context, it ends up decoding it for you. The important part is right here, draw, and then get a decoded image. The interesting thing about these decoded images, they look just like a regular UI image. There's actually no API way to say, oh, is this a decoded image or a regular non-decoded image? So you do have to keep track of this yourself. Like, I tend to keep a cache and map old images to decoded images. And these images also take up a lot of memory. So you want to be careful not to accumulate a ton of them and kind of kill your app with memory pressure. So this manual decoding, it is technically less efficient than just letting an image view do these things on its own. As you saw in that stack trace, that was the image view at the end of the run loop saying, OK, I need to decode these JPEGs and show them to screen. So this will happen for you automatically. And this is a little bit slower if you just did it on the main thread like you normally do. But the added benefit is that you can jump into a background queue, do this decoding, and this actually lets you go to a concurrent queue, decode 3 or 4 images at a time. And then when they're done, you can jump back to main and assign it to your image view. So one thing to remember when you're doing this kind of background decoding of images is that memory warnings happen on the main thread. And you may not realize this is a big deal, but if you're doing a lot of allocations in the background, you can actually end up missing these memory warnings. So your app gets notified, like, hey, clear memory. And the main thread will clear memory, but then you have all these background threads that are just allocating big images. And the system doesn't like that, so your app can get killed, especially on like an iPhone 5 and stuff. So to do this, you can just ping main. And these are the 2 examples, Objective-C and Swift. And all you have to do is call like an empty method or send an empty block, and then synchronously wait on main to clear its queue. Because if a memory warning happened, it'll be in the queue. And then you'll send this message, and it'll sit there and wait for main to finish clearing that memory. Then once it's done, you can go about your day and allocate your big images. So that's an important thing to remember. So here's the example of Catstagram again. And if you watch this time, as the images come in, the app doesn't have these big, big obvious stutters. So now all that decoding is happening in the background. And as you can see, we still have frame drops, right? So this is kind of the eternal game when you're doing performance stuff. You'll add some new code to your app, and then you may see your performance suffer for it. So you kind of have to dig in and see why that's happening. But in general, these are kind of the usual suspects when it comes to the average iOS app. The first thing is JPEG decoding, like we talked about. And the second is text measurement, also hierarchy layout, especially auto layout. I'm not a big auto layout fan. I know some people are. And then also object allocation, in Objective-C especially, is a big thing, bigger than you expect compared to doing simple things like math and adding numbers and stuff. So summary for the time profiler section. If you can do work in the background, you probably should. If it doesn't make your app any worse, then it's a good thing to throw it off of main. Just make sure it's not a UI kit object. Even like allocating a UI view in the background can, they're not thread safe, so you shouldn't do it. And instead, you can just use core graphics for this kind of stuff. And then when you're taking time profiler traces, make sure not to always ignore Apple's code, because there can be really important things in there, stuff that you should actually be thinking about. And then if you're doing this stuff, don't forget about memory warnings, so they are important. And then so sometimes you'll be profiling your app, you'll have performance problems, and you'll get to a point where you've kind of fixed all the problems that you thought you could fix using time profiler. So when you get to this point, a lot of times it's nice to break out the core animation tool, or at least something like it, to look at some things that can be causing your app to slow down, but not directly visible in time profiler. So real quick, there's this thing called the render server. In general, every time you make a UI view or put anything on screen, implicitly, behind the scenes, the system will create a CA transaction and then ship this off to a thing called the render server. So the render server is an out-of-process service. It maintains a copy of your view hierarchy, and then it's what takes care of all the drawing calls. So it does all the GPU drawing and all this for you. And it's a completely separate process, so it's not like inside of your app, but your app submits work to it. So when you have stuff, there's a lot of times where you can be writing UI kit code, and you won't really notice it. And there's, like I said, there's no way to notice these problems in time profiler. But sometimes you'll write code that indirectly makes the render server slower than it should be. So if you're doing that kind of thing, You can and could use the core animation instrument to kind of track these things down, but I was looking last night, and allegedly, it's deprecated now. So it's weird, though, because I opened up core animation instrument. It's still there, and they made a bunch of improvements. So I don't really get that. They improved it, and also they deprecated it. But they took all these debug options that were in the core animation instrument, and they actually integrated them into Xcode now. So it's kind of like the memory trace debugger and all that stuff. If you go into debug, it's kind of hard to get there. Debug, view debugging, rendering, you can find all these options that used to be in the core animation instrument. And so the first one we'll look at is coloring blended layers. And the cool thing about these debug options is that you can actually turn them on when you have a debug session going in Xcode, and then you can leave your app, and you can look at any app in the system and judge it harshly. So we're going to do that. That brings us to our next section, performance police. So some apps, they don't, So our first one up is iMessage. And as you can see here, we have this red. So that means we are blending the colors of these labels with the color in the background. And in case you don't know, if all that blending means is if you have, say, red and blue, and they're half see-through views, if you put them over each other, you'll get purple, right? So this is a calculation the render server has to do whenever it's drawing your views. And in this case, we have white text on a white background. But it is still doing this calculation. So rule number 3 is avoid unnecessary alpha blending when you can. To do this, it's pretty straightforward. If the subview has the same background color as the view that it's over, then go ahead and make sure it has an opacity of 1, and then make sure the background color is actually set. Most UI views default to a clear background color, so that's why these labels were showing as red, because they were clear background, but really it was white on white. So that's pretty common, and it's a super easy thing to fix in your app. And then the second one we'll look at is coloring off-screen rendered yellow. And so alpha blending is like a little hit, but it's also super easy to fix, so it's one of those things that you might as well do. But with off-screen rendered, this can actually be a much bigger performance hit, especially in scroll views. So in general, there's a bunch of things that can cause it. Here's Instagram. And if you've ever seen these little people circles, on my iPhone 6, I notice pretty aggressive slowdowns if I'm scrolling these. One thing that ends up happening if you do a lot of this performance analyzing is you kind of get an eye for when frames are being dropped. If you stare hard enough and long enough at an app, you can see when certain parts of it are a little slower than others. So this is one that I've noticed before. And that brings us to rule number 4. Don't use the corner radius property if you can avoid it. And this is actually partially fixed in iOS 11.3, I think. If you just have simple circles, you'll see green instead of yellow. And that means there's some fast path stuff they're doing under the hood. But if you have more complicated corner rounding, then it will still turn yellow, and it can be pretty performance intensive. So rounding corners is very similar to what we did earlier, but instead of just drawing with core graphics, we'll draw using a Bezier path. So here we can see we do a UI graphics image context, and then more importantly, we make a circle path, and we add the clip and draw using that circle path. So here we're just taking images and we're turning them into circular images. Then when you take them and throw them on an image view, you won't need to round the actual UI image view. You just have a circular image. And here's the third example. This is the Twitter profile screen. And as you can see, as it's animating the text out, this is real time. I didn't slow this down or anything. Done. And then when you try to scroll up the feed, it happens eventually. But so yeah, this may be the worst one I've seen, and this is on an iPhone 5, but even on my 6, it's pretty aggressively sludgy in this area. So I actually am not sure how they're doing so much off-screen rendering, but the only way I've found to really try and match this is to misuse the should rasterize property. So there's a property on CA layers that's called should rasterize. It's supposed to be there as a benefit to you. If you want to use it, you can use it to cache some of your textures. But the weird thing about it is that there's a bunch of rules around it. If you don't use it just right, it pretty much guarantees that your app will off-screen render on every single frame that it draws. So it's really easy to shoot yourself in the foot with it, and I think there's always better ways than using this property. So personally, I don't like it, so I would recommend not using it. It's really easy to fix. You just delete it. It's great. Nailed it. So yeah, summary for the core animation instrument is that you should avoid blending, avoid off-screen rendering, and there's a few other options in there for things that you can track, but these are kind of the big ones. Blending, make views opaque if it's possible. And then to avoid off-screen rendering, there's a bunch of things that cause it. Corner radius can cause it. Should rasterize causes it. Shadows can. If you're doing text shadows, then you can use the NS shadow class and an NS attributed string to do that properly. And if you're doing shadows around like a regular UI view, then you can just make sure to set the shadow path property, once again using a Bezier path. So the thing that happens with these off-screen rendering things is that basically you'll tell the render server to do something, and it won't have enough information to do what you've told it. So it ends up stalling the GPU, doing some calculations, and then figuring out what it needs. So that's why a lot of these fixes end up being like, oh, give it a Bezier path so it knows what shape to draw. So that's kind of the reasoning behind it. So yeah, shadows do it. And then the UI visual effects views, if you do like blurs and stuff, those are really GPU intensive and pretty risky. But if you use them right, they're pretty cool. And now we have the bonus stage. This is just some extra performance stuff, some things I've run into. And the first one is the camera slowdown example. So we have a camera in the Fuse app. You can make these fuses, right? And we've started adding some AR effects, some guides to help you take better fuses. And at one point, we had one of these super cool AR effects, but the performance in the camera was aggressively bad. And when I took a time profiler trace, I found that this super secret AR effect was the reason. And it was accounting for 26% of the work on every frame. But the interesting thing about this is that what was actually taking all the work was this. Hopefully it doesn't get, OK. What was actually doing all the work was this NS data. And if you look closely, you can see that all this NS dispatch data is doing is getting a chunk of bytes in a range, right? So this is a pretty, standard iOS-y thing. Pretty standard code thing in general. Get some bytes and move them. And when you run into a problem like this, a lot of times the way to solve it is to go lower level. Use C or C++. So in this case, we have an NS data, and we're moving bytes, right? Luckily in C, there's this nifty thing you can do. You can just use this function called memcopy, and it takes bytes, and it moves them. And even changing the code was not much different, right? We have a data, we get bytes, we give it a range. Instead, we switched out for a memcopy. We give it a range in a sense. It's a little bit of pointer arithmetic, but it's vaguely the same thing. And just switching these two lines, right? Switching from an Objective-C object to doing things with C, ended up when I redid the performance trace, we looked again, and this effect went from being 26% of the work that was happening to 0.6% of the work, just from that one line. So if you ever have you're stuck on this spot where you don't see what could be what's causing this other than a boring NS object type class. A lot of times, if you can jump lower level and avoid those objects, it actually ends up being aggressively faster. So that's kind of cool. All right. Another thing you can do, this is for Objective-C too, is imp caching. I think this one's cool, though, personally. So in Objective-C, as some of you may know, when a method gets called, it actually doesn't call this method directly. First, it does a lookup in a table to see where the function pointer for this method actually is. If you have a method that's being called a bunch, when you do a performance trace, you'll see this Objective-C message send function littered throughout your traces. And so if you see these taking up a significant amount of time in your time profiler trace, you can actually do a nifty trick where instead of just calling methods over and over again, you can grab a reference to the function pointer that's getting looked up and avoid the lookup altogether and just call this function directly. So this is the syntax. It is not very pretty, but once you get it down, it's kind of one of those things you can just keep copy and pasting maybe. But and then once you have the imp, you can just call it. And it ends up being roughly 2 times faster in general to call the function pointer instead of calling the methods. So it's super optimization, but it's cool and useful sometimes. And then, let's see. And the final bonus rule is if you're really desperate, you can just not use arc at all. And this, of course, requires Objective-C again. And this, I've heard we haven't even done this in our code, but I've heard stories of it making code 100% faster based on what the system is. So it is pretty interesting. There are ways to do it safely and not be a super headache. And then along with this rule, of course, comes don't use Swift. So it's a very offensive statement, I know. but in general, Swift is pretty hard to optimize. Objective-C, like these examples I showed, in my mind, they're pretty straightforward. And there's a lot of these kind of straightforward optimizations you can do. Swift is a little bit harder. And even once you've optimized it, it doesn't end up being as fast as C or C++ or something. So if you're desperate, you don't have to rewrite your whole app. You can take one little section that happens to be performance sensitive and do it in C or C++. So anyway, that's it for me. So if you want to go and look for some more learning, I really recommend this book, iOS and macOS Performance Tuning. It's by Marcel Weir. I hope I'm saying that right. German guy, I think. And it's a really interesting book. It's got a lot of cool performance tips from his time at Apple, so it's pretty cool. And then I also have a longer course about instruments on raywinderlich.com. There's a video course. And we go into the memory instruments, all of those. So a little more detailed. And then every year there's at least 1 or 2 dub videos about performance. So there's some really good ones. And then if you want to follow me, I'm Luke Parham on Twitter. I have a blog. I write sometimes. But yeah, that's it for me. Go forth and make Steve happy.